All right, let's dive into something that's right at the heart of computer science, asymptotic notation. Today, we're going to get a real handle on two super useful tools for figuring out how efficient an algorithm is. That's theta and little o. Let's get right into it.
So imagine this. You've coded up two different algorithms, and they both solve the same problem. They both work, which is great. But which one's better? Which one is actually faster? It seems like a simple question, right? But the answer can be surprisingly tricky. How do you even compare them in a way that makes sense, no matter what kind of computer you're running them on? Well, that's the big question we're going to tackle today.
Now, your first instinct might be, hey, I'll just pull out a stopwatch and time them. But as we're about to see, that simple approach, well, it can really lead you astray. We've got to dig a little deeper than that. See, the problem with just timing your code is that it's just not reliable. Your results are going to be all over the place. It depends on your processor, the programming language you used, heck, even what other apps you have running in the background. A beast of a gaming PC might make a really inefficient algorithm look good, but only when you give it a small problem. The second you scale that input up, that same algorithm will grind to a halt. We need a better way, a method that lets us talk about an algorithm's pure performance, totally separate from the hardware it's running on. And that better way is to stop focusing on seconds or milliseconds and start focusing on the rate of growth. This is the core idea behind what we call asymptotic analysis, and it's a real game changer. Yeah, this quote just absolutely nails it. What we really care about is how the running time scales as the input size, which we'll call n, gets massive. I mean, astronomically huge. For big data problems, this growth rate is everything. It's the difference between getting an answer in a few seconds and, well, an answer that would take longer than the age of the universe to compute. So to zero in on this growth rate, we make a couple of really smart simplifications. First, we just ignore constant factors. Who cares if an operation takes 2 nanoseconds or 10? At a massive scale, that's just noise. Second, we drop all the lower order terms. Think about it. If your runtime is something like n squared plus bn plus c, and n is a billion, do you really care about that bn plus c part on the end? Nope. It's basically a rounding error compared to the n squared term. This lets us see the true essence of an algorithm's performance. Okay, so we've got the concept down, but we need a language to actually describe this growth rate precisely. Our first tool for the job is theta notation. Think of theta as giving us an asymptotically tight bound, like finding the perfect sized glove for our function. Now, don't let the math on the screen scare you. I know, it looks a little intense, but the idea behind it is actually super intuitive. All this is really saying is that a function f of n is theta of g of n if, after a certain point n0, your function f of n gets permanently sandwiched between two scaled versions of g of n. There's a lower bound version and an upper bound version, and your function is just stuck right there in the middle forever.
And this graph shows it perfectly. You see how f of n is kind of wiggling around and doing its own thing for small values of n? But then, bam, after we pass that n0 point, it's trapped. It's completely contained between those two boundary lines. Its growth rate is essentially locked to g of n. That's exactly what we mean when we say g of n is a tight bound.
Let's make this real for a second. How would we actually prove that 1/2 n squared minus 3n is theta of n squared? Well, we just have to find those three magic numbers, c1, c2, and n0. The trick is usually to divide the whole thing by n squared to make it simpler to look at. From there, we just need to pick some numbers that work. You can see here that if we choose n0 to be 7, we can easily find a c1 and c2 that make the sandwich work from that point on. The key isn't finding the best constants, just proving that some set of constants exist. Okay, so theta gives us that tight bound. It's kind of like an equal sign for growth rates. But what if we want to say that one function grows strictly slower than another? For that, we need a different kind of bound, what we call a loose upper bound. And for that, we have little o. Now, the best way to get little o is to compare it to big O, which you probably already know. Big O is just a general upper bound, kind of like less than or equal to. The crucial difference is that a big O bound can be tight. For instance, n squared is O of n squared. That's perfectly valid. But a little o bound is always strict. It can never be tight. So while n is O of n squared, it's impossible for n squared to be O of n squared. Why? Because a function can't grow strictly slower than itself. The formal definition really shows you the secret sauce here. Remember, for big O, that inequality just had to hold for some positive constant c. But for little o, the inequality has to hold for any positive constant c you can possibly dream up.
You can make c ridiculously, absurdly tiny, and if you go far enough out on the n-axis, f of n will still eventually have to duck underneath it. It's a much, much stronger statement.
So what's the intuition here? It just means that f of n grows so much slower than g of n that it basically becomes insignificant as n gets huge. It gets completely crushed. For you calculus fans out there, it's the same thing as saying the limit of the ratio f of n over g of n is 0 as n goes to infinity. The growth of g of n just totally dominates. Okay, so we've got all these formal definitions, all this math, but why does any of this actually matter in the real world when you're just trying to write some code? It matters because it gives us this incredible mental model. We can think about comparing the growth of complex functions just like we compare simple numbers. I mean, look at this table. This analogy makes everything clear. Theta is our equal sign, big O is our less than or equal to, and little o, our new friend, is a strict less than. This simple idea gives us a precise and powerful language to talk about how efficient our algorithms really are. So let's end with a little brain teaser to make sure this all clicked. An algorithm with a running time of, say, 3n squared plus 10n is O of n squared, right? Because its growth is no more than n squared. It's also O of n cubed, because its growth is strictly less than n cubed. But why can that same algorithm absolutely positively never be O of n squared? The answer gets to the very core of what these notations mean. Think about it. Thanks for watching.